Um, I mean, both. I mean, the kids are terrifying, and like we even had like a couple like classes where it's all about like here's all the liability as a teacher that you need to care about, and it's like yeah, that's pretty stressful. And so I before that I was teaching like doing tutoring and stuff like that for community colleges, and I just like I like adults more. They're more annoying sometimes, honestly, but I like teaching adults. And then I fell into engineering more. So that very much the pay is hugely different. So yeah, yeah, yeah. I could see that. I mean, there were some really cool lessons like doing chemistry and different things like that for elementary school and middle school kids, which was very fun. Like those are great. I liked it. I could be creative, but it took me forever to come up with a lesson plan that's like engaging to everyone for what 45 minutes or so. Uh, that's true. That's true. It just takes a while to come up with new ones, and it's a lot of time investment for a lot of that stuff. It's good. It's great. It's just it's a lot, but I enjoyed it. I liked it for a little bit. Um, I had a couple friends who they also continued and then started teaching, and then none of them are teaching anymore now. They're doing either actuary stuff or something else. So I tell
Um,
myself eventually I'll go back, but we'll see. Yeah, yeah, it'd be a retirement thing or something for fun. Go become a emeritus teacher, and but
that is also my dream. Um, yeah. Chris, it's really nice to see you after it's been a while, a couple months.
yeah, no, we don't we don't have these anymore. Everyone wants to meet in the real world. Um,
Are you doing?
I'm not doing that. A Bay Area ish. I mean, moved about, gosh, I don't know, 60 miles away at the moment, but Bay Area still. And I used to come to when we would do meetups and things, or if there's events locally that different Rands folks show up to. It's just no, I'm not meeting anyone. Still have not met a single human in person for a social thing since last year, March. So
It's really a testament to your marriage.
yeah, I don't know. We're both homebodies, so it kind of it kind of works. I mean, less me, I guess, but I don't know. We're okay with that. I mean, our mother-in-law's still been with us since
Hmm.
last year,
You're still with you.
October. Yeah. Yep. Yep. It's still really hard to go back to China.
Yeah.
So at some point we might be filing for I don't know what, something. Um, because it's been about more than a year now. We'll see. And they'd love to stay. It's just immigration.
Yeah. Right. Um, What else is new?
Oh, I don't know. The new job, but you know about that. Um,
Yeah.
yeah, I started a new job in June or at the very end of June. So me and my wife both quit our jobs and got a new job, and we had this exact same end date and start date, and so it was great. So we had like a month off. Um, it was funny um, that we could coordinate that, I guess, but it was more of we were flexible on start dates, and so they're like, well, we're starting at the same time. Um, so that's been lots of fun, learning lots of things. Doing, I've been playing a lot more games with that computer now. I've been doing more, well, I've been doing, yeah, more not work stuff after working hours now. My my last place that was really tough, and so I'm kind of forcing myself to stop because I can easily be a workaholic. Um, very, very much so. Yep.
Yeah. Especially
Well, then
since
it's
you get
good.
to reward yourself with some cannabis after. Have a great live stream. Nice to meet you.
Fun. See
Bye.
ya.
Okay, here we are. Hello. Hello. We'll say hello, tap tap, and then we'll wave. Okay. Um, So, what are we saying today? Who's around? Anybody? We don't know? Me. That's me. That's me. I said hello from Restream, proving that it works. Probably live. Somebody's here. That's probably me watching. Okay, that's that. I may as well get started with or without y'all. Here we go. Desktop live stream. So let's start right here. So today we are talking about chapters 12 and 13. We can do a recap of the story so far. So we talked about the reasons for architecture. They are effectively, if you design your product carefully from the beginning, it will cost less to maintain and work with. And if you let complexity get out of control, you will have trouble. It will cost more. And we talked about solid principles. We've dealt with all of these now. Some of them were more compelling than others. We talked about programming paradigms, which are structured programming, object-oriented programming, and functional programming. You can go back and watch those. And here we are. It looks like it's just me tonight, so I guess we're going to do this the fast way, right? So chapter 12 was about the concept of components. I wasn't clear at the beginning of reading the book what the difference between a component and a module was, but we'll discuss what that means in a little bit. We also have something called component cohesion, which is, and we'll talk about it more in a little bit, but the cohesion aspect is trying to find a way to, how do we answer the question of what classes go into which components? And to know that, you have to understand what a component is to begin with. There were some additional resources listed in the original plan, just to remind you where this came from. OpenEdX they ran a clean architecture book club quite a while ago, 2019, so last year. 2 years. Oh my God, it's 2021. Anyways, they went through and ran there, and we based this series on their on their chapter layout. But as I'm going through and reading these things, I'm reading about one chapter in advance compared to the rest of you, and I found that 12 and 13 were really good together, so I moved them up. So you'll see that we're starting to deviate in the schedule. I've kept in the additional here. So this is the reason I started this tangent, is the 12 and 13 plus additional resources. They initially suggested the additional resources. I don't know that they were particularly that valuable, so I mean, they're here and we can talk about, so I went through them to see what it was and why we were interested in this. I think it's kind of just a summary of the things that we effectively have already dealt with. And this one doesn't even seem to be loading right now, which is fine because it wasn't the most compelling thing anyways. The other part of that was within that document, it links out to this one, which is a discussion from 1995 where somebody named, let me click that out, Jim Fleming of Unir Technology in Naperville, Illinois, 1995, says, I'm trying to come up with the 10 commandments of object-oriented programming. And here are some of the ideas that I think. And then if you go through, you can see the author of the book was participating in this discussion at the time, and he comes up with his list. This list very much mirrors the stuff that we've already talked about. And as you go through, I haven't gone through this entire thread, but what you can see is the discussion goes on, and there's probably a lot of nuance and interesting stuff that comes out of it. But I think mostly it just mirrors what is in the book now. So I don't think we have to go too deeply into that. I don't think it is really that critical in understanding of the content of clean architecture. And I particularly don't want to delay getting into the talk of components, because as I'm not going to say unimpressive, but as the previous chapters, some of the previous chapters were less compelling. I actually found that the components chapter and components cohesion chapter were actually more compelling, and they just start to hang these previous concepts together in a way that makes a lot more sense to me, and it gives me more confidence that the architecture chapter is going to end up being good. And I snuck ahead a bit, and there was some interesting stuff in the architecture chapter, but not important. Not important right now. We'll talk about it later. So, this chapter, so the summary of the components chapter, is really a history lesson about how the whole concept of components came about in the first place. And in order to understand where components come from, the author makes the case, and in fact, I don't know if I'm messing this up or confusing this with another talk on the same subject, but back in the olden days, when computers were run on punch cards and programs were series of cardstock with little holes in them in the binary pattern, people would design functions to be reusable. And what they would do, because your binary information was on a series of paper punch cards, they would be in a shoebox, for example, and then you would take that shoebox and you would put it up on a shelf, and it would be this would be a function that sorts an array. This function, this shoebox of cards, sorts an array. And you'd say, well, if I can sort one array, I can sort any array, and anything I can do, I'll just take this box, and when I need it, I will pull it down from the shelf. So they take these boxes, they put them on the shelf, and they would have a whole series of functional products that you could pull down, and they started calling it a library of functions, right? So that's where the term library comes from in programming. Quite literally, they were physical boxes of programs that you would pull off of a shelf and insert into your program in the right place. And so this is part of the place where components comes from. It's the design of that library of systems where where components are the units of deployment for the system, is what he says in the book. And so the units of the deployment might be one of these shoeboxes of functions, or maybe it would be a shoebox of a dozen common functions that you might use. Now, these things, these library functions that we have the concept is still around today, and they are our DLLs when we're working on a Windows machine. They are our jar files when we're working in Java. They are our gem files. The .o file in a compiled C program I believe the O probably stands for object or compiled object or something like that. So the O file. But additionally, things like if you're working in JavaScript and Node.js, your NPM module would be considered a component because components are independently deployable. You can use there are numerous cases where a single DLL is used in multiple places. There are numerous cases where the same NPM module is used by multiple program or multiple classes within your program. So the independently deployable aspect of these products means that if I have an NPM module called, for example, like left pad, if I have left pad, it's a function that I know adds blank space to the beginning of a string. It's a left padding of space, right? Or something like that. Well, if I discover a bug within left pad, I don't have to re-release my entire application to deal with that. I could actually just replace the one node module. So components are independently deployable. If I have a video game in Windows that I want to modify the behavior of, I do not have to replace the entire program. I can just replace one of the DLLs, the dynamically linked libraries, with which overwrites a function within the existing DLL, and all of a sudden it does something different. It's like if I took that shoebox of cards down off the shelf and I switched around the sort algorithm such that it's still sorted, but it did it using a method that was significantly faster. I could improve my program by swapping out that one box of punch cards without requiring a redeploy of the rest of the application. And so once things are independently deployable, so I can load them into my computer at any time, they can be developed separately. And that's the key, that's the magic of components. So here's the thing. And I don't have the book right here beside me, but there's another book that we're kind of talking about, and I see it right there, so give me just a second. We've got another book right here, which I have been talking about a bit, is The Philosophy of Software Design. And oh wait, hold on. Let me switch to solo mode so you can see the screen. See this screen? Here we go. So, and I want... That's better. I didn't know my whiteboard was up on the wall, but fortunately there's nothing interesting on it. So, The Philosophy of Software Design is actually, I can tilt that just perfect. Okay. So, I'll go back to the live stream. So, the first chapter in this book says, after the introduction, the first chapter in this book says that complexity is the thing that the introduction, the subheading of the introduction is, it's all about complexity. And so these concepts are mirrored by other people out in the industry. And so once you have an independently deployable package, it can be developed independently. And there's nothing more clear on that than an NPM module. If an NPM module is a component, there can be one group of people working on your HTTP module, or one group of people working on LeftPad, and they don't have to know each other. They just have to publish their pieces and you consume them. So this was particularly interesting in terms of the way that those library functions used to work. A developer, for any given function that we were creating, a developer would specify in the first line of code, you would say like star x 200 or something, and that would be a pointer to the location in memory where your code gets deployed. So you say star 0000, and it would go doop 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 doop, and it would fill up this space, right? That is the space reserved for my application. Load my application into memory in that space, and the spot where it loads within the memory system is hard coded. And if you think about this, it's really interesting because you say, oh, I've got this shoebox of code in punch cards where the memory location is hard coded, and I've got to pull this off of the shelf and I've got to plug it in. And if my code overlaps with the function library, I've got problems, right? You are overwriting the memory of a different function. And so this is the first part around why components. So one of the things, and so what happens when your functions, and these are images from the book, by the way, I've just reproduced them in Excel. The thing that happens when your application gets too big, it could start to overlap these function libraries that you're working with, or, oh, I didn't update this part of the image. Bad me. That's supposed to be 5. Anyways, I'm sure you're smart enough to figure out what that's supposed to be. So sometimes you would have to you would have to split the work that you have up over multiple points of functionality, right? So it's like you want your hard-coded memory location. And one of the things that happened within operating systems later on is function libraries got saved out to DLLs or jar files or things like that. And that's how components were born, because the operating system started to add a layer of memory management where the functions would be where the operating system decided where they would be, and you didn't have to hard code the location of your code. You would just have to you just run your stuff. And so people started creating these DLLs, these jar files, this sorts of things, and that's how runtime components were born. I think that was really, I feel like in terms of the chapter, it was really compelling from my perspective to understand where all of this grew from, if that makes sense. What is the underlying fundamental engineering problem that we're solving with each of these things? And so I thought that this was a particularly exciting and interesting chapter, but as you'll see, we're 20 minutes in and it's basically done. So I could either do a 20-minute show or I could move on. And that's why I was saying at the beginning that I've rebalanced the order of chapters, because we have more we can talk about in this week and using our time a little more efficiently. So component cohesion, the next chapter we're dealing with is about which classes get deployed within which components. So we have to first agree and understand that deploying components, or we first have to agree that our applications can be split up into much smaller pieces. The thing that gets really exciting when we start splitting our applications up into much smaller pieces is we can have different functional business units working entirely autonomously on just a tiny feature. And so you could have a finance team that just works on financial aspects, finance, and then finance might be separate from billing and credit card processing, right? Finance maybe wants the reports of the spending that happens, and they might have a team of programmers who do just things about getting those reports running, and then there would be another team that works on just the billing, and there might be another team that just works on user data, and there might be another team that works on, I don't know, that's enough. Each of these teams can independently deploy their portion of the application. So the question becomes, how do we determine how do we break up large packages into components? The rules he gives us, the author Robert Martin, gives us a number of, or we're given 3 top level principles that we can follow. REP, reuse release equivalence principle, the common closure principle, and the common reuse principle. So it's REP, CCP, CRP. Now, you'll see later, this gets interesting too. And the reuse release, so the granule of reuse is the granule of release. Now, not really super clear what this means when I read that initially. And so we're going to go through this. I think it can be summarized quite cleanly. The reuse of code would be one of those, like the shoebox of code. The thing you say, this is generic enough. So our earlier example was a shoebox that was an array sorting algorithm, right? That shoebox is generic enough that you can reuse it. So that should be the size of the thing that you release. The release is putting all of the code in a shoebox. The reuse is taking the box off the shelf and running your own array against the existing package. So the reuse of code, and so these are some of the highlights from the book itself. The reusing the code was one of the oldest promises that we got from object-oriented programming. People said, if we make these objects generic, we build things in this way, we'll be able to reuse large parts of our code. That's the story of inheritance, comes from that. Now, independently released modules must have version numbers such that programmers know what is in them. Now, now we go back to our big application that's divided apart across finance, billing, and user data. And these internal microservice or we'll call them microservices, these internal microservice or service teams or component teams, these component teams might individually release their product, but the might also need to communicate with somebody else. So finance might actually have to talk to billing or vice versa, right? So if the finance team has to update one of their APIs, they should release that with a version that will let the other teams, billing and user data, know that, to know what they can consume. So what if DLLs didn't have version numbers? We just swapped the function out and the method signature changes. What happens when you try and use an arrow function in IE6? Hint, you're going to have a bad time. This is, to my mind, one of the ultimate examples of version numbers, right? So let's look. When can I use the CSS grid in CSS? It's CSS. That's when. And so each of these, if you are using, I mean, this is version numbers. What could you do without having this information? When is this available for me to use? This is available for me to use in Chrome, in 57, in Firefox, in 52, and so on. And so now there should be some sort of overarching theme to any of the code that you release as a component. And classes or modules that are logically grouped together should be released together. Now, there's a famous judge. There's a case of a famous judge who says, "I don't know what offensive is, but I'll know it when I see it." And in Uncle Bob's book, The Clean Architecture, he says, this is weak advice. He says, these things that get released together should just make sense. But how do you know? How can you tell? Well, you can't know ahead of time. You've just got to, and there is so much art to this as well. So you've just got to know when to release something, and you'll know it when you see it. And so the next one, which is a little more, and this is kind of a feelings argument, if that makes sense. You're going to feel. Let me see my hair. Should have done that. Should have done my hair nicely today for you people. My one viewer. Thank you. Thank you, my one viewer, for coming by. It's cool. I don't mind. I'm doing it anyways. I have fun doing this. So the next up, we have this one called the Common Closure Principle. And it reads, gather into your components all classes that change for the same reason at the same time. And you separate the classes that change at different times for different reasons. So, I mean, on the face of it, so simple, right? So simple. But the question is, if it is that simple, why don't we actually do it, right? Typically, we, at least from what I've seen, from my experience, and maybe I am a terrible architect. I'm not. I'm actually pretty good. We put everything into one place and we don't worry about it. Now, here are some of the insights that we're getting from this. For most applications, we could go back to the list of the notes. For most applications, maintainability is more important than reusability, right? So you've got these large teams, you've got these big projects, you've got a multi-year goal, you've got millions of dollars on the line, but you've got a client base, you've got a customer base that is screaming out for features. And so you've got all of these problems, right? You've got to deliver quickly, but how can you do that if your code gets so complex that nobody can hold it all in their head anymore? Nobody knows what's going on anymore. So maintainability, this is the thing that we're saying here. Maintainability is more important than reusability. If the changes that we have are confined to a single component, then we only have to deploy one component. So if we've taken our app and we've broken up finance, billing, what was the other one? User data. We've got all of these pieces. If only something in finance changed, then we only have to redeploy finance. But if we've got this massive interwoven, oh no, everything's crazy, oh no, well, then we have to deploy everything every time. And that will increase risk. It will, increase workload. It just turns into a problem. So if two classes are so tightly bound that they always change together, they belong in the same component. If there are things that can be separated, you probably should. Now, where have we talked about this before? This is the single responsibility principle, but for components. And I think is that important? It's is the single responsibility principle for components not identical to single responsibility principle for individual classes? And I think it is. I think it's kind of, this is just one of those things that scales with the size of our system. So here's the last piece that we're going to look at for today. We've got the common reuse principle that says, don't force components to depend on things that they don't need. Now, it's obvious, I think, on the face of it, that you want to minimize your dependencies, and there really isn't much to talk about that. So here we go. And so the conclusion coming out of this chapter, and what do? We don't zoom very well on Firefox, do we? Okay, so what we wind up having with this system is, he calls this a tension diagram. So we group our things into the size of the unit that gets reused. So that should be those should be tiny, teeny tiny packages, right? Very small. But we also want to group things that go live together and change together. And so those are maybe slightly larger packages. There are a few more things in, and maybe you're not using everything. And then you want to split out this one's saying split things apart, and this one's saying put them together, and then this one's saying put them together in a different way. And each of these things is somewhat at odds with each of the others. And so if you work along this vector, if you work along these vectors, maybe you're going to have too many releases. Each of your teeny tiny microservices is getting deployed all the time, although it's just a tiny blip. As you may have experienced, or as I've experienced, even a tiny change somewhere can have massive effects across the entirety of your application. Now, if you work along this one, maybe you have too many components and to change, or it's hard to reuse any of the code and everything's bespoke and it's all copied and pasted off of each other, and it's all just a big nightmare and a problem to deal with. So it comes down to this, that the art of computer architecture comes into play around this point. And it's inevitable that you're going to be violating one of these principles anytime that you're doing something. So you're splitting something out. Oh, but those should be grouped together, or you're grouping things together and say, well, you can't reuse it if you're depending on something. So these things are pulling at each other and pushing each other in different ways. And it comes down to your judgment, your good judgment, to decide which of those rules to break at any given time. So a good architecture is one who finds a position that meets the current needs of the team. And again, back to I am working through this one, the philosophy of software design, in addition at the same time, and he's maybe a little more strict on that, but the needs of your system will change over time, and it's a really interesting thing to discuss the possibility or the situation of a startup versus a scale up or a proper business where you're trying to grow and expand the business. Now, in a startup, you can find yourself in a position where you need to get the features out the door. You need to ship your features quickly, and you need to make sure that you get release after release and functionality, because your company might run out of runway, right? Your company might run out of funding. Your investors might say, "Well, you're not developing fast enough. We need to see a payday." And so maybe this is the stage where you cut corners. And then you get it to the point where you have a stable business, and that's the point where you start to say, "Oh, maybe we have to rebuild our architecture a little bit for another one of the features of the type of business that we might run into, or as we want to grow, we want to keep getting features out, but we're going to slow down because things are getting too complex." That's where the art. And I'll bring up the image once again. So we've got these three zones of responsibility are in fact at odds with each other. See, the common reuse principle is saying split the things, and then the common closure principle says group them together. And so where in your program do you sit at any given time? And that's about the end of the week. There's not much else, but I did want to mention that in philosophy of software design, he has a great chapter, and maybe I should have done notes on this, but I only read it today. So let me take that off. So in the philosophy of software design, he says he makes this distinction between strategic programming and tactical programming. Now, tactical programming is doing the least amount of work in the fastest way in order to make your feature functional, versus strategic programming, where you take 10 to 20% more time to think about how you're going to write it, to write it in a clean way. We'll just say clean. To write it in a clean way. And the expectation is that if you work over time and grow a little slower, you will maintain your speed for significantly longer, because by going strictly tactical programming over time, your development or your productivity, the complexity of your system scales to the point where you cannot make changes to it anymore. So this is coming up again and again, that the only way to go fast is to go clean over time. And it starts out that tactical programming is faster, but in the long run, it slows down. And so we go clean overall. That's the week. Thank you for watching the rerun. We didn't really have a lot of chat today, which is okay. That happens. And I hope you have a great week, and come back again next week. Bye. Okay, stop streaming. Where do I click? It's compelling content, right? I found the button. Okay.